Hi, today I'm going to talk about sex-linked traits. So what I want to go through is just a brief description of what that means and also look at a couple of conditions that are sex-linked. And then we'll go to the whiteboard and try a few problems for sex-linked conditions. Move my face here. So sex-linked traits are also called X-linked traits. And the reason they would be also called X-linked traits is that they are found on the X chromosome. So you'll remember that males have chromosomes that we call XY. They have one X chromosome, and females have two X's. So males, if they get the condition on one of their X chromosomes, then they're going to have the condition. Whereas a female, if she got the condition on one of her X chromosomes, then the other one can take up the slack and compensate for it. So many more males are affected than females. Okay, so one of these conditions is color blindness. Not all kinds of color blindness, but red-green color blindness is sex-linked, and I think there's another night blindness that is also sex-linked. But anyways, it's considered to be an X-linked condition, and therefore this is the kind of situation that might be possible here. So here I've got a male who does not have the condition. So he's got a healthy X and a Y chromosome. Now here's a female who is a carrier. She has one affected allele, and her other X chromosome is healthy. So she would be a carrier. She would not have red-green color blindness, but she would be able to pass it on to her offspring. So this doesn't mean they're going to have 4 children. This is just looking at all the possibilities every time they have a child. This is one of the scenarios that they might get. So they could get a boy who gets his healthy X chromosome from his mom and gets a Y from his dad. Now the Y doesn't matter. I colored him all in blue because he's got the healthy X chromosome and that's going to make him healthy. Now they could get a female here, a female that got dad's X chromosome, which is healthy, and mom's healthy blue chromosome. And so she would be perfectly healthy. She wouldn't even be a carrier. Another possibility is that she could have gotten the healthy allele from her dad, the healthy X chromosome, and the affected X chromosome from her mom. And so she would also be a carrier like her mom. And here's the final boy. Now he's got the X chromosome from his mom, and doesn't really matter about the Y. He got the Y from his dad, but the Y has no bearing. So I colored him totally pink because he's going to have the condition. In this case, red-green color blindness. Another common condition that we look at in sex-linked disorders in humans is hemophilia. Keep in mind that there are several types of hemophilia, and I'm not going to give you a big lesson on all the different types and modes of transmissions and ways you can get hemophilia. But one type of hemophilia is going to be sex-linked, and it's going to follow this exact same pattern. So the general mode of transmission is going to be where you have an unaffected male and a carrier mother, and they're going to have a son who has it. So hemophilia is a disorder where the blood can't clot properly, and this is quite a serious condition. It results in heavy bleeding that won't stop even from us if you get a little tiny cut. Okay, here I've set up a Punnett Square and I've done it for you, where father is colorblind and mother is a carrier. So here's the father at the top, and he's carrying color blindness on his X chromosome. And the mother, she's got two X chromosomes and she's carrying not hemophilia, I'm sorry, color blindness, the same pattern. Okay, and she's carrying it on one of her chromosomes. So there are possibilities for female children, and you see the female children are here, is that the female children can either get the affected allele from mom and the affected allele from dad and have color blindness. So that would be the only way a female is going to get this, is if she gets it from both parents. And the other possibility is that she gets dad affected X, but she gets the healthy X from mom, in which case the healthy X will compensate for the affected X. And she will not have hemophilia, but she will be a carrier. Now, with the male children on this side, it just depends which X they inherit. So, because they're both going to get, both possibilities are they're going to get the Y from dad, so to make them male. So if they get this X from mom, the affected one, they will have hemophilia. If they get the healthy X, then they won't. So 50% of the male children will have hemophilia, and 50% of the female children will have hemophilia in this case, and 50% will be carriers. Okay, I'm going to actually move to my whiteboard now and do some extra problems with you on the whiteboard. So grab some scrap paper and we'll do some together. Okay, today we're going to talk about sex-linked traits. So sex-linked traits are often also called X-linked traits. So you'll see that kind of used interchangeably. And the reason they're also called X-linked traits is they're carried on the X chromosome almost exclusively. So let's just take a refresher look at how sex-linked traits sort out. Okay, so as you will remember, females have two X chromosomes and males have an X and a Y. You can see I'm starting to make a Punnett square here. So when meiosis happens, the eggs will have one X or the other, and the sperm will have an X or a Y. Okay, one or the other. So it's always the sperm that determines whether the offspring is male or female. So if this sperm here were to fertilize, then you would end up with two X's, and here, if it was this sperm, you're going to get an X from the mother and a Y and an X and a Y. Okay, so you can see it's 50-50. It's always 50-50 whether there's a male or if it's a male or female, because you're going to get just as many sperm with the X as you do with the Y. Okay, so the reason I'm telling you this is because in X-linked traits and doing those kind of Punnett squares, you do need to use the sex chromosomes since they're carried on the sex chromosomes. So in this case, unlike other circumstances in life, I guess, it's of a benefit to have two X chromosomes, to be female. Because when you have two X chromosomes, if something happens to one of these X chromosomes, then this one can pick up the slack. It can fill in the information that's missing. Because really, a person just needs one X chromosome for life. So if you have two X chromosomes, you're much less likely to have a sex-linked disorder. Whereas if you're a person who is male and you only have one X chromosome and there's something wrong with that X chromosome, then you're cooked. You've got that condition. So females are generally going to be carriers rather than having the condition. It doesn't mean a female can't get the condition. If she inherited a mutated copy on both of her X chromosomes, she could have the condition. But you can see why that would be less likely. So the pattern is usually that females are carriers and they pass the condition along to their sons. And then the son, his female children are going to get his X chromosome, so they're more likely to be carriers. And his male children are getting his Y chromosome, so they aren't going to have any problems there. So that's the usual pattern with X-linked diseases, is that they go from mother to son to daughter to, and that's the mother, and then to son again. So that's how it usually works. So when we're doing a Punnett Square with an X-linked condition, and there's quite a few of these, color blindness is a really good example. Color blindness is an X-linked condition. So let's use that one. Another one you'll probably come across is hemophilia, which is a disease in which the blood doesn't clot very readily, and it can be really, really dangerous. But let's use color blindness since nobody gets hurt there. Okay, so, you know, if a female is carrying color blindness on one of her X chromosomes, it really doesn't matter which one you put it on. It's going to work out the same. If you know she's a carrier, just put it on one of her X chromosomes. And here we're going to have a man who does not have color blindness. He's not color blindness. So what's going to happen here is a female child getting an X from dad and this copy from mom with the color blindness on it. Well, she's going to be a carrier as well. Now they'll also have a possibility that the child will get this X chromosome from mom, and then she won't have color blindness and she won't be a carrier. Now this boy here, he got the good X from mom and the Y from dad, so he's okay. But this boy, he's got the X with carrying the color blindness and the Y from dad, so he will have color blindness. So usually when you get questions on Punnett Squares like this, they'll ask you about male and female children. So you can say it'll say something like, what percentage of their male children will be colorblind, and in which case the answer would be 50%. If it just said what percentage of their children would be colorblind, well, I guess it would be 25%. If they said what percentage of their female children would be colorblind, the answer is 0, because none of their female children have color blindness. They're just 50% could be carriers, but that doesn't mean they have the condition themselves. Okay, so how about if I put a few sex-linked conditions on Punnett Squares on, you stop the video and try to solve them, and then continue on. So I'm going to put on, this time I will make it hemophilia. The woman is a carrier and the man has it, which is unlikely, but let's just say that happened. In this case, let's say the woman is a carrier. Well, let's make it color blindness again. No, I shouldn't have done that. Oh well. Okay. Color blindness. And the man does not have color blindness. And then let's try a female who is colorblind and a male who is not, and see what happens. Okay, so you can pause and do these problems, and then we'll try them together. Okay, hopefully you had a chance to work these out.
let's start here. So hemophilia, this girl would have it because she'd get it on both of her X chromosomes. In this case, she's getting it from one parent, but not that from the other. So she's a carrier. And here we have a male who's going to have it because he's got it on his only X chromosome. And here we've got a male who's perfectly healthy. So 50% of their male children, or another way to think of this is every time they have a male child, 50-50 whether that male child has hemophilia or not. And same with the females. 50% of their female children would have hemophilia. Okay, now we've got a female carrier and a healthy male. So we've got a female carrier and a healthy female. We've got a male with color blindness and a male without. So this is, we've already done this problem, I just realized, but anyways. 50-50 for their male children having hemophilia. None of their female children will have hemophilia. Okay, now we've got the unlikely situation of a female who is colorblind and a male who is not. So here she's got a healthy allele and an affected allele, so she's a carrier. Same here. She's got a healthy one and an affected one, so she's a carrier. Here, that's an X, and it's affected, and he's got color blindness, and same thing here. There, he's affected. So we would say, if we were asked what percentage of their male children are affected with color blindness, we would have to say 100%. All of their male children are going to have color blindness, and that makes sense because male children get their X chromosome from their mother. Female children get one from each parent, right? So 100% of their female children will be unaffected but will be carriers. Okay, so I'm going to leave that there for now and we'll do some more practice on this.